So the head of the royal family passes away, and we need a successor. How do we figure it out? Turns out we can use discrete math to answer that question. This lesson depends on the idea of an ordered, rooted tree. First of all, tree. Remember, a tree is a graph where it's fully connected, but there's no cycles. In other words, there's always, to get from one point to another point, there's exactly one path. A rooted tree means that there is one point, one vertex from which all the branches flow. And we talked about leaves of the tree being the bottom level. Now, ordered is the one that we haven't talked about yet. And an ordered rooted tree means that whenever I create this tree, all right, so I've got a tree that I'm busy creating here, and I'm getting down to the leaves, and there we go. How about something like that? All right. Now, an ordered rooted tree says that, first of all, there's our root. Here are our leaves. It's 3 levels. All right. But the order means that these siblings have a specific order. I don't know how you might want to order it. Maybe there's some sort of an identifier, a number. Maybe it's alphabetical order. Maybe it's ease of use. I'm not sure. The idea, though, is that from left to right, there is a specific order. Now, you can't say that you haven't seen something like this before, because whenever we do anything in English and we start talking about this idea of an outline, you've probably learned about the method of numbering your outline, and there's a couple of ways, but the decimal outline format, like this one, is a tree. It's not as easy to see if it were just a tree, but this decimal outline is a tree. In fact, if we go to the view of a tree, we can see how the order in which we use that decimal format gave us the order in which they appear on the tree. Now, this is not the only order that we could have used. For example, we're talking about pets here. We could have, instead of ordering them alphabetically like we have here, we could have ordered them by popularity or by ease of keeping them or any number of things, maybe size, who knows. But the idea is that the left to right, there is an order to them. Now, ordered rooted trees are a very common mechanism for storing information on the computer. Why? Well, because whenever it comes to computing, we need to have ways to process individual items. We need to have ways of searching, sorting, and so forth. And an ordered rooted tree will give us that capability, because we need to have a way to reliably be able to hit every single vertex, make sure that we hit it exactly once, make sure that we process it exactly once, and the ordered rooted tree gives us that mechanism. So when traversing a tree, so this idea of traversing a tree is that we have to visit each node or vertex exactly once. And we need to have a process to do this. And whenever I say visit, it may just be, to search, or, is this the right one? Is this the right one? Is this the right one? Or maybe process. We need to do a particular process for this vertex. We need to do a particular process for this vertex. Or just simply, count, who knows? But the idea is that we visit each one of those vertices exactly once. The question is what order do we do it in? So that's what this lesson's about, is the processes that we use to traverse the tree so that we visit each node exactly once. For example, let's talk about this order of succession. Maybe we have a royal family tree here, right? And the royal family tree is all the children and siblings and so forth of every member of the royal family. Now, if we have this ordered in a particular way, we need to figure out, okay, the head of the royal family can't for some reason go on with their duties anymore. So how do you figure out what the next in line is? Well, maybe if this is oldest sibling to youngest sibling, and then their oldest children to their youngest children, you may do something like go down this branch and then go down this branch, and then if Go down this branch, and if they can't do it, continue going down that branch. If they can't do it, go up and down, and then up and down, and then maybe nobody in this little subtree can do it, so you go and check the next sibling and so forth. And so there's a process that you can visit each one to figure out if they're qualified to be the one to take on the crown. Picture this particular scenario, something you're a lot more likely to experience. You need to figure out or clear some space on your hard drive. How do you do that? Well, you may go, do you just delete a top level directory and just say, oh, I can delete this directory and to heck with everything that's in it? No, what you probably do is you go all the way down to the lowest folders, check to see if it's okay to delete this, maybe delete this, go up, go back down, and keep going up and down in order to figure out which folders need to be deleted. So maybe this instead represents a hierarchy of your folders on your computer, and I want to come up with some space. And so I go down, can I delete this one? Yes or no. Then can I delete this one? Yes or no. Can I delete this one? And maybe if I've deleted all of those, can I delete this? And you can do a process of visiting each folder one at a time. Unlike the royal family where you started at the top and went down, in this case, you're probably going to start at the bottom and work your way up. In the 1950s, David Huffman, a computer scientist, came up with this process of compressing data by taking the string that you wanted to compress and generating a unique tree that identified exactly how we would code each one of those characters. The reason this works is, well, in the 1960s, they came up with a table called ASCII that allowed us to assign a 7-bit value to each one of the characters. So capital letter A through Z, lowercase letter A through Z, all the punctuation marks, the numbers, a couple of control characters, spaces, a control character to say whenever we were at the end of a line or the end of a file and so forth. The problem is with every character requiring exactly 7 bits, then for example, if you had 100 characters, then you needed to find 700 bits in memory in order to store those characters. David Huffman's Huffman code said, okay, for a particular string, there are certain characters that occur more often than others. And based on that string, we can develop a unique table or a unique tree, a unique graph in order to pass through and figure out, okay, this pattern can represent this character, this pattern can represent this character, and so forth. So I have created a string and asked a tool to develop the Huffman code tree for me, and there it is. So we've got this tree, and so you start out, you haven't received any bits, and you start out, and when you look at this, you say, okay, if I receive a 1 followed by a 1 followed by a 0, well, that represents an S. All right. And then once you've finished reaching that character, you go back and you do the next one. You can tell from this tree which characters are used more often. For example, the space, there are 4 of them. The lowercase m, there are 3 of them. The lowercase h, there's 2 of them. The lowercase a, there's 3 of them, and so forth. Now, this tree is structured so that each character, there's only one way that you can get from the root of this tree down to the bottom, down to the leaf, for a specific pattern of 1s and 0s. There's no way one pattern of 1s and 0s can get you to a question. Which one of these characters does it represent? So let's get a string of 1s and 0s and see if we can't decode it using this tree. 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, 1. I guess I should have made a shorter string. 1, 0, 0, 0, 1, 0, 0, 1. And I'm probably breaking in the middle of a character here, but here we go. 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. There we go. There's our string. Now, what does this equal? What does this represent using this table right here? Well, we start out with a 0, so we go down the table and goes down to the 0. And then we have a 1, so we follow the 1 down, and then we follow a 1, and we reach a leaf. And that leaf represents an M. All right. Now, so we go back up to the top. We've got 1, so we follow 1 down. then we go to 0, follow the 0, and then another 0, and that gives us a leaf to A. And by the way, this is not a capital M. This is supposed to be a lowercase m. All right. And then we go 1, 1, 1. That brings us to the leaf T. And then we go 0, 1, 0. That brings us to the leaf H. 0, 0, only 2 jumps. This is a space. And then we have 1, 0, 0. That brings us to an A. And then 1, 0, 1. That brings us to I. 0, 1, 1. M. So the 0, 1, 1, we got 2 of those patterns, right, so far. 1, 0, 1, 1, 0, this is an S. 0, 0, that was a space, right? And sure enough, I did break this in a bad spot. Let's change that 1 and move it down here, because I know that we've got a 3-digit character coming up here. 1, 0, 0. So 1, 0, 0. That's a lowercase a. 1, 1, 1. That is 1, 1, 1. That is a T. And then 0, 0 is a space. And then 1, 1, 1. That brings us to a T. And then 0, 1, 0, H, and then 1, 0, 1, I, and then 1, 1, 0, S, and then 0, 0 is a space, then 0, 1, 1, that's an M, and then 1, 0, 1, that's an I, and then 1, 1, 0, that's an S, right? And then 1, 1, 1, that's a T. Sorry about that. And I'm sorry about, that's the best I could do. What I was looking for was a limited number of characters so the tree wouldn't be that big. And I came up with math aims at this mist. In other words, what may be out there looks a little cloudy, but math is going to clear it up for us. All right. Now, this took what? 62 bits. So there are 62 bits there. If I had stored this as bytes, 8 bits at a time, it would have taken 176 bits, significantly more. Now, you may say, okay, well, since every single time that I want to use one of these Huffman codes, I have to also send the information of the tree along. Yes, there is information in the tree that does need to be included, which would, especially for short strings, counteract our savings. But when you talk about long strings and you have a Huffman code, then you'll find a much simpler or a much more compressed way of sending your data. So the question is this: how do you search a tree? Well, like any complicated problem, the best thing to do is to break the problem into its pieces. So let's just say I have this tree, and this tree I need to search. I'm just going to create this rather interesting complex tree, and in fact I'm going to label the nodes, and we'll just say A, B, C, D, E, F, G, H, I, J, K, L, M, N. All right, so there are my nodes. Now, the question is what process do I use? And it has to be a rather rigorous process. Now, first of all, like I said, any complicated problem, what you're going to do is you're going to break it into smaller components. So you could actually look at this and say, okay, there's a huge tree, but you know what I could do? I could assume that this tree is actually made up of 3 subtrees that are all connected to a root. All right. And in fact, this subtree right here is 2 trees connected by the root B. And this little tree right here, this subtree right here, is actually 2 trees, K and L, connected by a root E. So we could break this down so that an individual vertex is a tree in itself. And then by seeing the order in which we broke that down, figure out the order in which we can go ahead and search this. Now, there are a number of ways that we can break this into subtrees, keep breaking it down into subtrees, and make sure that a process of examining that order in which we traversed them, make sure that it gives us the ability to visit every node. There are 3 ways of doing this. There is something called preorder traversal. There is something called inorder traversal. And then there is postorder traversal. All right, and each one of those gives us a process in which we examine the nodes. Let's begin with preorder traversal. First, you visit the root. All right, that's the step 1. So in this case, you visit this root, A. All right, you process it, you search it, you do whatever it is that you're supposed to do. The second step is to visit the subtrees left to right. What does that mean? Well, we're visiting this tree, this whole tree. You start by visiting the root. Now, once you've visited the root, then you go left to right, the subtree for B, the subtree for C, and then the subtree for D. You visit them. Well, how do you visit the subtree for B? Well, you begin by visiting the root. And then it has its subtrees, the one with E and then the one with F. You start with the one on the left, and that one is E, and you visit that tree. Well, how do you visit that tree? You start by visiting the root, and then you visit its subtrees. Now, its subtrees are K and L. You start with the one on the left, you visit K. Then, when you're done, you've reached the bottom, there's nowhere else to go, then you visit E's right subtree, L. Now, once you've finished visiting the whole tree of E, you go back up to B and you visit its left one, its next one from left to right, which would be F. So in that case, we are actually getting an order. And the order for this guy would be first A, then B, then E, then K. Now we've reached all the way to the bottom. So we go back up to E. We don't visit it again because visiting it again would indicate that we would visit it twice. So we go down to its child, which is L. We come back up. We've already visited E. We've already visited B. So we come down to B's next child to the right, which is F. Now we go back up. All of B's children have been visited. So we go back up to A. Its next child was C. It has 2 children, G and H. You go to the one to the left, that's G. Visit that root. Then you go down to its left, that's M. Now you can't go any further, so you go back up to G, but you can't visit it again because that would be visiting it a second time. You go down to its next child to the right, that's N. Come up, G's already been visited. Come up, C's already been visited, but we need to go down to C's children to the right, which gives us H. Then we go up to C and A, both of which have been visited. Go to its next child to the left or to the right, and that's D. And then D visits I, and then you come back up and go down to J. And we get this order of visiting nodes. This list right here is just the order in which the nodes were visited. And this is a lot like that royal family figuring out the order of succession. Now let's talk about in-order traversal. Well, now in-order traversal says first visit leftmost tree, subtree. So we don't visit the root. So you go down. Now this tree, we're visiting this tree, we visit its leftmost subtree. And we go to this subtree and we visit its leftmost subtree. So we get all the way down to a leaf and we visited it. And in this case, it meant we got all the way to K. Now once you get to K, you have to come back up. And after you visit the leftmost subtree, then you visit the root. And then after you visit the root, then visit remaining subtrees left to right. That's a lot of, I don't know if I got that all on camera or not, but I tried. All right. Now this one process is a little bit more difficult. You go down, so we're not going to visit A, we're not going to visit B, we're not going to visit E, we're going to go all the way down to K. We come up, now we have visited the leftmost node of E, so now we can visit E, and now we can visit the left next to the right, so that's L. So we have K, E, L here. Now that we visited this entire subtree, we can visit the root of that subtree, which is B. And now, left to right, now we can visit the children on the right and going right, so that's F. Now we have visited this whole subtree, and we go up and we hit A, we can visit A. We go to the next child to the left, C. We don't visit that root until we've visited all of its leaves. So we go down to G, can't visit that root, we have to go all the way down to M. Come back up, now that we've visited M, we can now visit G. Now we can visit its children going left to right, which is N. Now we come back up. G has no more children to the right, so we come all the way back up to C. Since C's leftmost child has been visited, we can now visit C. And now we can go down and visit H. Now we come back up. We've already visited A once. And since we've already visited A once, we can't visit it again. We are just going to continue visiting its children left to right. We've visited B, we've visited C. Now we need to visit D. And so, well, not visit D, but go down to the subtree of D. Now, since D has children, we visit its leftmost child, which is I. It is a leaf, so we go ahead and put down I. Go back up, so now that we've visited the leftmost root, or leftmost subtree, now we can go and visit the root, which is D, and then we can visit its children left to right, and J is the only one left. So notice there is a very different way of examining those guys in order. Now let's take a look at post-order traversal. In this case, we first visit subtrees left to right. So we begin with the subtrees. We don't look at the root yet. After we have visited all the subtrees, then we visit the root. Now, how might this look in terms of the ordering of the nodes that we have created up here? Well, hopefully I have enough room in this screen. Maybe not, but I'll go ahead and post it in my editing if I didn't make it on the screen. So, don't visit the root, visit the subtree first. Well, the subtree has a root with subtrees, so we visit the subtree first. And notice we're still staying to the left, and it's always going to be left to right, all right? Then we go down to E. Well, E is a root of subtrees K and L. So we first visit K. So just like with the in order, we visit K first. Now, we go back up, but unlike in order, which says we visit this E first, no, we go up and back down to visit L first. Then once all the subtrees of E have been visited, now we can visit E. Come up. All of the subtrees of B haven't been checked out, so left to right we go from E to F. Now once we get to F, we can go back up. All of B's subtrees have been visited, so we can now visit the root, B. Go up to A. All of its subtrees have not been visited, so we come down to C. It has subtrees, so we go down to the left one. G has subtrees, so we go down to its left one, to M. Then we come up, G's subtrees haven't been all visited, so we go down to N, left to right. Up to G, now G's subtrees have been visited, so we can visit the root G. Go up to C, down to H. Up to C, now all of C's subtrees have been visited, so we have C. Up to A, now we have to go left to right, hit D. D has subtrees I and J, so we visit I and J. Then go up to D. And finally, now that all of A's subtrees have been visited, we go up to A. All right, so we've got K, L, E, F, B, M, N, G, C, I, J, D, A. All right, now I'm going to erase this because what I'm going to do is show you, well, there's actually a trick to make this a little bit easier. Turns out that there's a little trick we can do. If you start at the root and you draw a path that keeps very tight and tucks into each one of these little nooks and crannies, and I am apparently, I should have made a larger graph, shouldn't I have? All right. Oh, okay. So remember, you've just got to tuck into each one of the little nooks and crannies, go up and visit the inside of each one of those nodes. And it turns out there are tricks that we can use with this path in order to figure out preorder, inorder, and postorder. And hopefully, I will get the right ones for each one of these. Now, the trick is, first of all, with preorder, we're going to visit each node or vertex on first pass. Okay? And what that means is that as soon as you pass a node, you're going to visit it. So I am going in this direction. So we come down here and I go A, B, E, K, and then come up. I've already visited E once, so I don't visit it a second time. And then I come down to L, come up. I've already visited E once. I don't visit it again. I've already visited B once. I don't visit it again. But I come down to F, and then I come up. I've already visited A, but I haven't visited C. I haven't visited G. I haven't visited M. Come up. I've already visited G. Come back down, N. Come up, all those have been visited, but H has not. Come back up, A has already, but D has not, I has not, and J has not. And so there's our list. A, B, E, K, L, F, C, G, M, N, H, D, I, J. And if you look back at the previous board, you'll see that that's exactly the same sequence we got whenever we were visiting nodes using the rules. Now, in order. How does in order work? Well, first you visit leaf on first pass. All right. So I come all the way down here. There's a leaf. There's a leaf. First pass, I visit it. All right. And each parent on second pass. All right. So you'll notice that a lot of these parents, for example, let's take a look at B here. B is passed 1, 2, 3 times. So you visit it on the second one, all right? Specifically, and in fact, this is probably most important with A. You visit A, you don't visit A on the first pass, but when it comes back up, you visit it on the second pass, but you don't visit it again on the third or the fourth pass. That's how it works, all right? So we come all the way down here to K. We come up, we've passed E once, now we're passing it a second time, so we can grab E. L we pass on its first turn. E we don't visit again. B, however, this is the second time we've seen it, so we do B. Come down to F. Go back up, past B, this is a third time, so we don't visit it again, but we are visiting A a second time, so A is going to be added or visited. Then C is not a leaf, G is not a leaf, but M is. Then we come back up, this is our second pass to G, so we add it. We hit the leaf N, G a third time, no, but C a second time, so C is visited now. H is a leaf, so as soon as you visit a leaf, you add it. C is visited for a third time, no. A is visited for a third time, so no. D first, no. I is a leaf. D is now the second time, so we visit it. J is a leaf, so we add it. We come up, and A has already been visited, so we don't visit it again. And we get KEL, BFA, MGN, CHIDJ. That is exactly the same thing we got on the last, on the other way of visiting, all right? Now, let's take a look at postorder. Postorder, basically, you visit each vertex on the last pass. The last time you go past it on its way back to the parent. All right. So if you look at this, and it may not be obvious right away, but what you're saying is you're going to do it on the last pass back to the parent. So you come all the way down here to K, and then you go up to E. It's not the last pass before heading back up to the parent of E, which is B. So you come back down to L. Now we come up. This is the last pass, the pass that is on the far right side of E on its way back up to B. So now you do visit E. Go up to B. No, it's not the last pass, so you visit F. Now we are on our way back up to the root of B, so we do visit B. We come down. C is going to have another pass, so don't worry about it. G is going to have another pass, so don't worry about it. M, we're heading back up towards G, so we do. N, we head back up to G, so we do. G is headed back up to C now, so now we visit G. C, we come down to H. It's headed back up to the root C, which is headed up to the root A. Then we come down to I. It heads up to D, then back down to J. We visit J, and then we visit D on its last visit on the way up to A, where we've got the connection to A. Is this the right one? Well, K, L, E, F, B, M, N, G, H, C, I, J, D, A. That's exactly what we got on our last try to figure out the post-order visiting for this tree. Let's get rid of this tree. Now what I'm going to do is I'm going to have a binary tree to represent an expression, a mathematical expression. And I'm going to show you the different ways of traversing this tree allow us different ways of representing this expression. So this expression is going to come down like this. And let's see how, remember, it's a binary tree. So, and in fact, it's a complete binary tree, which means every single vertex has two subtrees coming off of it. So here we go. There's my subtree. So let's do division, minus, plus, times, and then all the leaves are actually going to be numbers. We'll just put A, B, C, D, E. All right. Now what this represents is first you have A minus B is divided by C times E plus C. And so the expression is actually, the full expression is A minus B divided by C plus D times E. All right? And so there's the expression. And in fact, this is in order notation. And it is referred to actually, whenever we talk about this binary tree representation of an expression, we are actually referring to this as infix notation. And it's what we're used to seeing. We're used to seeing our operators like division, subtraction, addition, and multiplication. We're used to seeing those operators between two operands. All right. That's just the way we write our expressions down. We're going to see there may actually be a better way to do this. And so if I were to do this with traversing the tree using in order notation, what I would get was I'd come down here to A, and then come up to minus, and then come down to B, and then go up to division, and then go down to C, up to plus, down to D, up to multiply, and down to E. All right? Now, this is exactly this, right? Except for one problem. We've got order of precedence here, or, the order of operations. PEMDAS, is it? This would say we would do this operation first, then do this operation, then do this, add this to this, and then subtract that all from A. We've lost our parentheses, all right? And by losing the parentheses, we actually have changed what the expression represents. What we're going to see is that with a post-order or a pre-order traversing of this tree, we actually don't need parentheses. Back in the old days, back in the 70s, Hewlett-Packard made a calculator called the HP35. Where did they come up with the name 35? Well, the 35 actually means that it had 35 keys on it. Now, back in the old days, the processors were maybe not as capable as they are today. And the type of operations for this calculator, this is actually referred to as a stack machine. And the stack machine is one where what you do is you first put on one of the numbers, then you put on a second number, then you do the operation. You see, there's no equal sign, there's no equal key on that calculator, there's an enter key. So you would do, for example, if you wanted to do A minus B, you would enter A, enter. And then you would enter B, enter, and then you would hit minus, enter. And that process, first A, the first operand, second operand, then operation, very common. And this was actually referred to as postfix or reverse Polish notation. And that was how this calculator was used. Turns out that this is exactly the method in which we use post-order traversing of this tree. So let's do it this way. You remember post-order said you visit the leaf first. And so I visit A, and then I come up and visit B, and then I do the minus. And then I come up here, come down, do C, come up, down to D, up, down to E, then up to the times, then up to the plus, and then up to the division. So this would be entered into the calculator as, it would be entered AB minus CDE times plus divides. And that is, believe it or not, that's the way that this particular operation works. Now, if we were to do this by hand, what you would do actually is look for this pattern where you've got an operand, an operand, an operation. There's another one right here. And in fact, by looking for that pattern, we see that AB minus, that is already handled in the parentheses. And then DE times, handled once again with the order of operations. Now, once you do this operation, you substitute it with whatever the result was. Let's just call the result F, okay? So that would be F, and then the result of this operation would be G. And now you have FCG plus divides. Now, do you see that pattern again? Operand, operand, operation, CG plus. So then you add C and G together, and you put the result in. Maybe that's H, and now we have FH divides, FH divides. And it makes it so we don't have to have the parentheses included in our expression because the order of operations are already preserved by the order in which we traverse this tree. Now let's traverse this tree using prefix notation. All right. Prefix notation, or the pre-order traversing of the tree, instead what you do is you visit the node first, so we do divides, and then we visit the node minus, and then we visit the leaves, A, B, and then we come up and visit the node first, plus, and then go to C, and then come up, visit the node first, times D, E. And we see that once again, we've got this pattern, except the pattern is backwards from what we had with the postfix notation. You've got operation and two operands. So operation, two operands. And then here you have operation, two operands. And once again, we have our order of operations without having to conclude the parentheses. So we substitute F for AB, A minus B. We substitute G for D times E, and you've got divides F plus CG. Now we've got operation, two operands. That is this item in the parentheses right here. So these guys we replace with H, we get divides FH, and so F divided by H, that takes care of the whole piece, and we have preserved our order of operations without a single parenthesis in the mix. So before wrapping up this lesson, let's do a couple of examples. Let's see, how about divide minus 14, 4 plus 3 times 1, 2. All right. This is going to be prefix notation. Now you notice I've got an operand, I've got an operation, two operands. So there's one of those patterns we're looking for. I also have one down here. Operation, two operands. So 14 minus 4, that's 10. So substitute the 10 where that operation occurred. Then I've got plus 3, and then I've got times 1, 2. So 1 times 2, that's 2. Now, the only other place in here I've got that operation, two operands, is right here. So we do divide 10, and I've got 3 plus 2, that's 5. Now I've got 5 divided into 10, that's 2. So without parentheses, I was able to do 14 minus 4 divided by 1 times 2 plus 3. All right? Let's see if it works with postfix notation. In postfix notation, that same expression would be 14, 4 minus 3, 1, 2 times plus divides. All right? Now, hopefully you can see where those patterns exist again. So I've got operand, operand, operation right there. I've got operand, operand, operation right there. So I've got 14 minus 4, that's 10. And then I put the 3, copy the 3 down. And then the 1 times 2, that's 2. And then I've got plus divides. I only have one place in here where I've got operand, operand plus. That's the 3, 2 plus. So 3 plus 2, that's 5. So I've got 10, 5 divides. Now I have 10 divided by 5. That is equal to 2. All right? So hopefully this discussion about how to traverse a graph helped you understand the way a computer might navigate one of those trees. It also helps to understand that just about all of our problems have trees or graphs involved in them somehow. So understanding how to traverse a tree can be really important whenever it comes to implementing any sort of computing solution.